It's me. It's Mr. Maltby. It's Tuesday. It's 4th period. It's 5th period. It doesn't matter. It's AP Calculus learning time. Woo! What's up, class? I miss you so badly, and I'm so excited that we get to spend a little bit of time together from the comfort of my home. Let's do a quick little roll call. What's up, Emmy? What's up, Conley? What's up, Kaylor? What's up, Georgia? What's up, Lucas? What's up, Lucy? What's up, Leo? What's up, Oliver? What's up, Niall? What's up, Walker? What's up, Megan? What's up, Rebecca? Sorry, I'm trying to wave. What's up, Dava? What's up, Ed? What's up, Evelyn? What's up, Grace? What's up, Michael? What's up, Neil? What's up, Ariella? What's up, Alma? What's up, Orla? What's up, Sach? What's up, Abby? What's up, Max? What's up, David? What's up, Sade? What's up, Gassan? What's up, Leo? What's up, Isabella? What's up, Rose? What's up, Eli? What's up, Maddie? What's up, Nicole? What's up, Sam? What's up, Mackenzie? What's up, Raleigh? Yes, I'm reading off the roster. What's up, Cam? What's up, Zach? What's up, Im? What's up, Madeline? What's up, Darren? What's up, Sophie? What's up, Andrew? What's up, Jocelyn? What's up, Caitlin? What's up, Logan? What's up, Catherine? What's up, Kylie? What's up, Audrey? What's up, Jesse? What's up, Matt? What's up, Audra? What's up, Caleb? Really hope I didn't forget anybody. Let's go. Hopefully, we're still into learning today. So, you know where we're starting. Just like yesterday, we're just going to read through what the video is going to be about. And then I'm going to say bye-bye. Number 1, get a calculator. We are going to use our calculators today, partly for things that you have to use a calculator for, but also for just a way to show you just some time-saving tricks with the calculator. That'll be a big deal in this unit. And then we're going to read the agenda. So go get a calculator. Like stop. Get a calculator. And then let's read the agenda. Most of today is going to be me just kind of working out parts of the assignment and explaining it. But in theory, you should take page 4, which is Tuesday, and just do the first page except that thing at the bottom that's like 100% perfect description formula. Hey, read that page, answer that question, stop the video. I will make a face that you can hit pause to. Are you ready? Yeah, but if you didn't hit pause yet, just I really do want you to actually spend 3 minutes. Don't just sit here like a zombie. Like, I'm gonna do kind of most all of the work. Can you please just read that page? Just please. Okay. We kind of have 2 main things we're doing today that are extensions of the fact that we are now in the area business. We are in the total change business. We are in the multiply business. And because we're in the integral business. We're going to talk more about the meaning of area. So if we're in the area business, what are we learning when we're in the area business in context? And then the other thing we're going to do is look at some ways to approximate area. Finding area is tricky. Approximating area is a little bit easier. And that'll make sense as we get into today's problems. So we're going to learn how to explain the meaning of area. We're going to learn to approximate the area using our notes for today, which is rectangular approximation method. And there'll be just kind of some quick notes that you don't have to write down. We will kind of explain the notes by working through the work today. And we're going to use tables of function values in order to facilitate this. So rectangular approximation method is what we're going to learn to do today. I'm going to show you how to use tables and write out and organize tables in order to do this in a very efficient, effective way. So we're going to use tables in order to facilitate this technique. We're going to learn how to find the exact value of area using our calculator. So if you remember, all fall we were doing second trace 6. It was the way of kind of doing calculus in your calculator and doing derivatives in your calculator. We're going to look at second trace 7, which is kind of the other calculus button. And it's the button suitable for the business that we're in now, the area business, the integration business. And then the last thing we're going to do is learn what's on the pop quiz. And I haven't entirely decided exactly what what I would quiz on from this lesson, but I have a pretty good idea. And by the end of the video, I will tell you. Right. And so we're going to explain our basic goals are we're going to explain the meaning of area, and we're going to learn to approximate area using LRAM, RRAM, MRAM, which are these abbreviations for rectangular approximation method. And we'll get into more of those later. It's time for me to go. Before I do, I'm just going to apologize now that how I've planned the lesson, it's going to be a lot of me writing with the trackpad onto the screen, onto the worksheet. So that's going to be a little sloppy. That's just how it is. All right, let's take one last look at the snow. And that's going to be that. Bye-bye, Mr. Maltzby. All right, y'all. So, hey, let's do this. Let's talk more about the meaning of area under a curve. And this is the thing that I've asked you to go ahead and read over and do. So you have read, or you are pausing now. You have read through all this, and you've answered question 1. So question 1 was pretty easy. The graph below depicts the rate at which oil is draining from a leaking ship. The Y values represent gallons per hour. So let me draw with my mouse. Gallons per hour. Yep. And the X values represent hours, or T, or whatever we're calling our independent variable. That's our hours. In the first blank space below, try to write a good sentence describing what does the area under the curve from x equals 0 to x equals 10 possibly represent. In other words, if, and once again, you're going to have to excuse me, if you found the area of everything kind of trapped in blue here, right? If you found the area of this, oops, what would that area mean? Finding it is much more difficult than explaining its meaning. So, if you recall yesterday, we talked about how area is always base times height. So if you take gallons per hour as your height and multiply by your base, so we're doing base times height or height times base, those units eliminate. Hey, and what you get is the units for this area is gallons. And if we're talking about this ship here, we want to say something like this. It's the total number of gallons that leaked from the oil ship. Oh no, be careful. We don't know that it's an oil ship. We know it's oil in the ship. The total, let's call it the total amount of oil in gallons which has leaked from the ship from t equals 0 to t equals 10 hours. And what I would say is, whatever your sentence is, I hope it's got the word gallons in it, and I hope it doesn't say anything like rate. So you didn't have to say that's the total amount of oil. You could say it's how many gallons have leaked. So let's do another one. How many gallons have leaked from the ship from t equals 0 to t equals 10 hours. And I'm going to get lazy and copy paste. If you use the words gallons per hour, it's wrong. Or if you use the words leaking or draining, you're describing a rate of change, so it's wrong. We're not in the rate of change business anymore. If we're in the area business, we're in the total change business. So what we're going to do is just write kind of a cookie cutter formula for the meaning of area. And I wouldn't call this like notes for the day. This is more just a principle. The area under the curve and then here we go. Total change in x units times y units. So in other words, whatever we had here and whatever we had here, we multiply them. It's the total change in x units times y units from x equals a to x equals b. And this is I guess a formula for writing a sentence regardless of situation. So if this is squirrels per tree, and this is tree, you'd say it's the total change in squirrels from 2 trees to 10 trees. Anything like that. All right. So we are now in the area business, which means we are now in the total change business, or the total amount of increase or decrease. What I would like you to do is scroll to the next page a little before me and read that situation, and you'll be asked to find the area under the graph. Give it a shot. Hit pause. Okay, I guarantee all of you did not hit pause, but that's okay. I understand. It's very hard to actually like watch a video, stop when I say stop, do what I say. I know you're just trying to get through this as best you can, so I forgive you. Okay. So the graph below depicts the rate of change in temperature of a turkey in the oven. I know my sentences are all kind of a little clunky, and I apologize that. For various times t. So we got t equals hours, and C of t is degrees. Make a circle. Degrees Celsius, that's a C, per hour. Yep. There we go. What does the area under the curve represent? Well, first we want to get the units right. So if we have degrees Celsius per hour and hours, when you multiply these units, you get degrees Celsius for your units. And we could think back to our cookie cutter sentence. And we're going to do 2 sentences. We're going to do cookie cutter, and then we're going to rephrase it in a way that human beings might actually talk to each other. It's the total change in degrees Celsius from t equals 0 to t equals 6 hours. Now this is not wrong. This is kind of correct. We just said total change in x units times y units from A to B. But let's remember to say something a little more meaningful. It's the total change in degrees Celsius of the, So what it really is it's going to be the increase in turkey temperature measured in degrees Celsius for the first 6 hours. Either of these sentences are correct. It's just that total change in degrees Celsius doesn't really describe what's happening, whereas, it's the increase in turkey temperature measured in degrees Celsius. So the dependent variable is how quickly the temperature is increasing. The area, now that we're in the total change business, is the total amount of increase. So it's kind of a cumulative effect. All right, let's talk for a minute about how to find area. So I hope we can agree that this graph has an area, and I'm going to do another one of those amazing drawings. So if we found the area of everything in blue, or everything kind of between the blue, right? So all this space, whatever the area is here, that's the total increase in turkey temperature. But if I asked you to find this area, we have a problem. This is not a geometric object. Your whole life, every time you've had to do area or volume, it's always been something geometric where you could lean on a geometric formula. This is not a geometric object, so finding the exact value is not going to work. What we're going to do is use what's called an approximation method. So we are not going to answer by hand or without a calculator. We're not going to be able to answer without a calculator the actual area. We're going to come up with an estimation method or an approximation method, and that's going to get to our notes. And here's what I'd like you to do. I'm going to clear most of this. You have some space. You actually need to copy this down into the space. I guess this is going to be one of the things that's going to be on the pop quiz is, did you write this on your worksheet? So take the worksheet, write down LRAM, left rectangle approximation method. We'll talk more about that. But then write down the question, which is approximate the area under the curve of f of x equals x squared from 0 to 6. So that area I just drew using 3 sub-intervals. And we'll talk about what that means. and go ahead and draw this table. And please hurry up because I'd like to switch over to our notes for the day. All right. So here are our notes. Today we're learning a technique called rectangular approximation method. And it's just a process for estimating the area bounded between a function and the x-axis by finding the sum of the area of rectangles. The base of every rectangle is delta x, the base of every rectangle, delta x. So delta x is the base, and it's equal to b minus a over n. We'll explain what that means. And the height of every rectangle is determined by the value of f of x within the domain of the rectangle given certain parameters. Okay, here's what you really need to know coming from this. We're going to use rectangles. They're all going to have a base, and they're all going to have a height. And the function is going to help us determine the height. And let's go back and draw some of these. So LRAM, left-angle approximation method, using 3 subintervals. So in other words, subintervals is your number of rectangles. I'm just going to add that. Okay. Here's what we're going to do. We're going to draw in some rectangles. And I'm just going to go ahead and kind of start one now, and we're going to narrow it down in a moment. All right, so I'm going to grab my little rectangle program. And I'm going to draw a rectangle. And this rectangle is going to exist from 4 to 6. And I'm going to go ahead and I'm going to start some rectangles. This one's not done. We haven't decided how tall we're going to make it. This one's going to be from 4 to 6. We'll end up making it a little bit taller in a moment. This one's going to be from 2 to 4. And this one's going to be from there to there. So that's going to be our 3 rectangles. All of them have equal width. So all of their delta x's, let's go ahead and actually calculate that now. And you'll have to forgive me as oops, let's not do that. As I kind of pause to get fancy with the math. All right, let's calculate our delta x's. Oops. Well, if it's from 0 to 6, that's a total of 6. So 6 minus 0 divided by the number of rectangles, which is 3, equals 2. So that's where we decided that all these are going to be 2 units wide if we're going to have 3 of them. What we need to now do is pick the height of each rectangle. So what left rectangle approximation method means is that the height of the rectangle is equal to the value of the function on the left edge. So I'm going to redraw these, and I'm going to go right to left. And what I'm going to do is I'm going to stop when the rectangle reaches the function on its left edge. So if you watch the left edge of the rectangle, we haven't reached the function yet. We're almost there. We're almost there. Boom, right there. So y'all see how the height of the rectangle now intersects the function at the left edge of the rectangle? We'll do it again. So we know we're going to be 2 wide. And we should stop when the left edge of the function of the rectangle hits the function. By the way, if you're drawing this, do not draw this. I want you to draw a very specific problem on this worksheet, and it's not this one. So erase whatever you have. And then we need a third height. And I don't know if y'all notice, but right away, our function has a value of 0 at x equals 0, so we can't really go up at all. If we go up, we've immediately passed the function. So this rectangle is going to have an area of 0. It's our third rectangle. There it is. All right. So here's what we're going to do. We are going to add up the area of these 3 rectangles. How we're going to do that, though, is to fill in some values on a table. We'll do them visually first. So each rectangle has a base of 2. And each rectangle has a different height. So you may be able to look over here and see the height of this rectangle is 16. Do you know the easiest way to get that? It's to recognize, oh, this is x equals 4, and this is the function t squared. So, hey, what would be the value of the function at x equals 4? It would be 4 squared. So that's 4 squared. So we know, okay, this rectangle is 16 units high. This rectangle, remember, this is x equals 2. So right here, this kind of corner is 2 squared. So we know that this rectangle is 4 units high. And lastly, this rectangle, 0 squared is 0. So this rectangle is 0 units high. Here's how I would really like y'all to record this. We're going to kind of reboot and undo some of this. Anytime we have these, I want you to make a table. And on that table, you should always put your a value, or your starting place. So in this case, we're starting at 0. And then once you know your delta x, you should kind of add values of x to the table until you reach b. So we know if we're 0 to 6 and delta x is 2, our first rectangle exists from 0 to 2. Our next rectangle exists from 2 to 4. And our last rectangle exists from 4 to 6. So those are the key values that we're going to put into our table. Under that, we're going to put in the function's value. So if it's t squared or x squared, down here let's put in 0 squared is 0, 2 squared is 4, 4 squared is 16, and lastly 6 squared is 36. And we're not going to use that value for this problem, but we will a little bit later. So now, oopsie. Now when we redraw those, hey, we know that first rectangle is supposed to exist from 0 to 2. And it's going to have a height of 0. That next rectangle is going to exist from 2 to 4, and it's going to have a height of 4. And lastly, that last rectangle exists from 4 to 6. And it's going to have a height of, and I know I can fill it in a little bit better than that. It's going to have a height of 16. Here's what I would like you to do. Make sure you filled in this table. And I do want you kind of diagramming from column to column. These are basically like the metaphor for our rectangle. This first guy, this is rectangle 1, whose height is 0. This is rectangle 2, and since we're doing left, we look at that left number, the height is 4. And that last one, the height is 16. Okay. And then we just kind of multiply and add them up. And I'm running out of space, but I think I can squeeze it in here. Let's go right here. Oh, let's actually make some room. Our area is, well, it's 2 times 0 plus 2 times 4 plus 2 times 16. We add that all up, and what we get is, I believe, 40. So 40 is the area of these 3 rectangles. It's our estimation for the actual area and the total change of the turkey. It's not a good estimation, right? We did not do a good job filling up the area. It's a bad estimation, but it is nevertheless an estimation. What we're going to do real quick is change the question. So if you have room on the page, and you don't have to do this, we're going to change it to right ram. We're going to do right rectangles. And I'm going to get to delete, I think, everything. So this time, we would still have x squared. We would still have 0 to 6, and we're still going to use 3 rectangles. But this time we're using what's called a right rectangle approximation method. So we are going to draw our rectangles a little bit differently. This time, that rectangle that exists from 4 to 6 does not stop when the left edge intersects the function. No, no, no. It keeps going until, you guessed it, the right edge intersects the function. So this time, that rectangle covers all the space we need and more. Our rectangle from 2 to 4, still 2 units wide, but this time we don't stop here. That would be a left, because the left corner is intersecting the function. No, 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 no. We keep drawing until the right corner of this rectangle would intersect the function. And then lastly, this rectangle, this time it will have an area because the right edge is actually right there. Now, once again, we're going to add up the three areas, but this time we're going to rely more on our table. Hey, we know that first rectangle exists from 0 to 2. And if we look right there, oh, look, it's got a height of 4. That next rectangle exists from, sorry, that column thingy is super annoying. That rectangle exists from 2 to 4. It will have a height of 16 because it's under the right edge of our rectangle. And our last rectangle exists from 4 to 6. And if we look under the right edge of that rectangle, it will have a height of 36. So hey, look, that's a height of 36. This rectangle is a height of 16. And this rectangle is going to have a height of 4. That's a 4. 4 is tough with the trackpad. All right, hey, let's add up our areas. So in here, that first rectangle is 2 units wide and it is 4 units tall. That next rectangle is 2 units wide and 16 units tall. And that last rectangle is 2 units wide and 36 units tall. Bringing our total up to, I believe, 76. So our first estimation was the total change in turkey temperature was 40 degrees. Oh, I'm just kidding. It's not 76. That's not enough. We need to add 6 onto that. I think it's 108. Uh-oh. I'm doing math. I'm doing math on stream. You're never supposed to do that. We're going to cheat. 112. Got it. It's 112. So when we use left rectangles, we got an estimate of 40 degrees. When we use right rectangles, we got an estimate of 112 degrees. As you can imagine, neither one of these is correct. The answer is going to be somewhere in the middle. Now, let's go back and look at left RAM one more time. You may be asking yourself, like, okay, I get that every rectangle has area, but the area of this rectangle and the actual like total area are so far apart. What's up with that? And the answer is we're not using enough rectangles. This is kind of that general theme of calculus that, hey, the wider amount of the x-axis you take up with an estimation, the worse that estimation is. So let's actually take a look at what we're going to do next. We're going to jump in here. We're going to be looking at the same graph. It's the turkey graph. And unfortunately, I got to reset some settings. All right. So n equals 3, that means 3 rectangles. This was the first question we did. The scale's slightly different, but we got a sum of 40. Don't worry about that. It's because this is not actually 6. It's like 6.000, whatever. We got a sum of 40 using our rectangles whose left edges intersected the function. We got a sum of 112 using our right rectangles where each rectangle had the right edge intersect the function. Well, let's look at what happens if we used more rectangles. So let's just increase the total number of rectangles by 1. If we use 4 rectangles, hey, we get a little bit higher total and we're filling up a little bit more space. We use 5, we're filling up that space even better. And lastly, if we use 6, oh look, now we're actually taking up a good percentage of that space. So if we found the area of these 6 rectangles, it's a pretty good estimation for the area of the curve. And so this is what we're going to do. We're going to jump back to the worksheet. We're going to work out the sum of these 6. And then we'll probably also do the sum of these 6. So these are the right rectangles, where each rectangle's height is when the right edge of the rectangle would intersect the function. All right, let's do it. So I'm going to scroll down. I've got this question actually set up down here. So we got the same graph, but this time we're going to do a left rectangle approximation method of same function, 0 to 6, so same amount of time, but 6 subintervals, so an in value of 6. So we want to figure out our delta x, and I'm just going to call it delta x this time. It would be 6 minus 0 divided by 6, because that is the number of rectangles. So it's b minus a divided by n, and that works out to 1. Every rectangle is going to have a width of 1. So let's start saying, okay, the first rectangle will be from 0 to 1. The next rectangle will be from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and lastly 5 to 6. By the way, if you're ever wondering, like, what's a trick for how many columns, n plus 2. So if it's in a 6, I just kind of note, okay, make 8 columns and everything will fit nicely. The last one, I think it was 5 columns because it was 3 plus 2. Let's fill in our function values. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, and 36. And let me tell you the truth, most of the time you are not going to be drawing on graphs. What you are going to be doing is kind of diagramming a table. That first rectangle is 0 to 1, the next rectangle is 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. Now if we want, we could go ahead and draw them in. We've seen what they look like. These are left rectangles, so their left edge needs to intersect the function. And right away we can see it's not filling up the space perfectly, but it is doing a much better job than 3 rectangles. There we go. And then our last rectangle, of course, exists from 0 to 1, but 0 squared is 1. All right, let's do our area. So if we look at our table that we've diagrammed, we know that first one is from 0 to 1 with a height of 1. So it's 1 times 0. The next one is from 1 to 2 with a height of 1. So I always like to use this little diagram to say, oh, if I'm doing left rectangles, I want to look under the left edge. So 1 times 1 plus 1 times 4 plus 1 times 9 plus 1 times. And we're not going to use 36 for this because our last rectangle exists from 5 to 6. The left edge would have a height of 25 when it intersected the function. So we know, okay, that's y equals 25 right there, which makes sense looking over. And we add all this up. And I tell you what, let's do it like this. We have a common factor of 1, so we can factor out 1 and just do 1 times 0 plus 1 plus 4 plus 9 plus 16 plus 25. And we can just add those up and get our value. And now we multiply by our common width of 1. Hey, we get 55. All right, pretty good. Let's clear this out. And here's what I'd like you to do. This is, hey, guess what? This is kind of, it's not pop quiz, but this is like required, kind of like a pop quiz. I want you to find the RAM approximation from 0 to 6 using n equals 6. So in other words, this right here. I want you to sketch this onto your paper. Make sure you have a table that has 8 columns because I want to see that and I want to see the diagramming. And then come up with an answer. I'll give you a hint. I think the answer is 91. But show the work for it. Okay. That's something I'm going to ask you to do on your own. Hey, we're just going to wrap up with a little bit of like, hey, where's this going? Imagine that instead of doing 6, because we don't think 6 does a good job, We wanted to increase that. From 0 to 6, hey, what if we used 12? Look at this. Suddenly 12 does a great job of filling in that space. And you can probably imagine, hey, what would fill in the space perfectly? Well, as n approaches infinity, I think we can agree the area we get as an estimation approaches kind of perfect. All right, let me back down to 12. This is that thing about your calculator. We're going to jump in and look at our calculator and have it help us out. If I was doing this, honestly, the hardest part would be just drawing 14 columns. That would be the pain in the butt. I would grab my calculator, type y equals into the menu, and then go to my table setup and, hey, you know what? 0 to 6, 12 rectangles. Each rectangle is going to have a delta of 0.5. And then what I would do is just jump over here and, hey, look, here are all the numbers that I need to put in my table. There's the top row of my table. I would have, I think, 14 total columns, including kind of the label columns. And I would go all the way till I hit n equals 12. I'm sorry, till x equals 12. And these would be all the f of x values that I put in my table. So just recording these would be the hard part. I just wanted to point that out. We'll practice using that on Wednesday when we get back. Here's the last thing I want to show y'all. This is the graph. And if we do n equals 12, we estimate the total change in temperature of the turkey is 63 degrees. But if we press second trace 7, lower limit of 0, upper limit of 6, look at this. 72 degrees. That is the total change in turkey temperature. So look, why don't we make that the last part of the pop quiz? I'm going to give you a function. I'm going to ask you for the area under the function. All that you're going to have to do is type a function into y equals. And then I'll show you where that feature is again. I need to do a quick little clear draw real quick. So, all right. All you're going to have to do is type in the function. You do want to make sure your window includes what are called your lower and upper limit. So 0 to 6 fits inside the window 0 to 7. And then you press second trace, and it's option 7. Second trace 7. We're starting at 0. Our area ends at 6. And there it is. So how to find exact area with your calculator. That'll be the other part of the pop quiz. This video ran long because this is actually what we're doing for the next couple of weeks. We're going to be studying area, talking about its meaning, and also estimating it with rectangles or finding its exact value with our calculator because we are now in the area business. Here's what I think I just need you to do. Let's take a look at our learning goals. Yep. Hey, last thing I want you to do is also make sure you do an RAM 0 to 6, n equals 6. So I want to see 6 rectangles drawn where the height of the rectangle, I'll do one for you. Let's go 2 to 3. The height of the rectangle is inspired by where the right edge would intersect the function. And then find the sum of those, add them up. I think it's 91. And do the T-Pain problem. Oh, did I cover MRAM? Hey, let's cover MRAM. MRAM is simple. Let's make this. So I'm going to morph this into a problem we need. We're going to use mid. That's what M is for. M is for mid. 3 subintervals. N equals 3. So, and let's draw them. So we're back to n equals 3, so they're too wide. That would be a left. That would be a right. A mid would be when the middle of the rectangle. So watch here, right? The middle's right here. A mid is when the middle of the rectangle intersects the function. So something like right there. That's a mid rectangle. That's a mid rectangle. and that's a mid-rectangle. And this is pretty easy to do. I have my table down here. That first rectangle exists from 0 to 2. 1 is the height of that rectangle because 1 is in the middle. F of 1 is in the middle of 0 and 2. That next rectangle exists from 2 to 4. It has a height of 9 because F of 3 would be the middle of 2 to 4. And that last rectangle exists from 4 to 6. And it has a height of 25 because F of 5 would be the middle function value from 4 to 6. Okay, good. I taught MRAM. It happened. So I'd like you to do the T-Pain problem. I would also like you to answer that question I mentioned. Don't forget what the pop quiz is. The pop quiz is, I think I just want to see the work and then also, yeah, so just see the work that I assigned and also just that one thing about using your calculator. I would just point out, hey, n equals 6. So after you read this problem, the first thing you want to be doing is drawing 6 rectangles, kind of metaphors for rectangles onto this table. Once you do that, the LRAM, RRAM, and MRAM are pretty easy. Don't forget delta x is 2. All right, I'm on a boat. Bye.